to have fractures and more fractures as you increase in length scale. But it's due to the presence of fractures. All right, okay. So I'm getting a little bit away of our topic, but let's come back to it. All right, so we know now what are the new surfaces that we need to take into account for this elastoplastic model, and we know what is the basic response depending on where you do the loading. So let's write the equations now for these two surfaces. What is going to be M? M, by definition, is going to be the ratio of Q over P at failure or at the critical state line, right? So if I'm at the critical state line and at failure, let's assume in this case that as we have seen before, the sigma 1 divided by sigma 3 is going to reach a maximum value of 1 plus sine of friction angle divided 1 minus sine of friction angle. And let's say the friction angle it's 30 degrees, just to put an example. And so that's going to result in maximum sigma 1 is going to be equal to 3 sigma 3. Right? You follow me in that? So this one is 3, right? So that's why sigma 1 is going to be 3 times sigma 3. So at failure, what is going to be Q? By definition, we know Q is sigma 1 minus sigma 3, right? And what is P? Sigma plus 2 sigma 3. Let's do as you said, plus 2 sigma 3 divided by 3, right? So if at failure I have sigma 1 is 3 sigma 3, then let's move this 3 over here to the top. How much is going to be this? How many sigma 3s? 2 sigma 3s, and this? 5 sigma 3s. So what is going to be 6 divided by 5? 1.2. So the parameter M is just a function of the critical state angle. And now I'm going to add this CS over here. And if that critical state angle is, say, 30 degrees, then your M is solely a function of that. And in this case, it's 1.2. But if you had some other friction angle, you will have to do the same operations in order to get the value of M. But M is basically a friction parameter. Okay? So then M is related to the critical state line slope. All right. So we have that one. What about that ellipse? What is that function going to be? That's going to be F, and it's a yield surface. And we're not going to develop it from scratch, but I'm just going to tell you what that function is. It's a function of Q, it's a function of P prime, and it's a function of P0 prime. Right? In order to define the size of that ellipse, I need to know what is P0 prime. So the function, the yield surface function is going to be Q squared minus M squared times P prime, P0 prime minus P prime. whenever this is equal to 0, that means that it's at yield. Yes?
Isn't that not strictly true? I mean, on the left-hand side, it's the critical state line that determines yield, and on the right-hand side, it's the yield surface that determines yield.
That's correct. Yes.
So would it be to say that it's, so if it crosses the yield surface at a p greater than p0
Yeah.
over 2, then it's a yield. If it crosses it at a p less than p0 prime over 2, it's a yield.
So sometimes this equation is valid for this side. And it's also valid for that side in this model. But sometimes you have some other equations from this side. But that's why I'm not getting into this side for now. But I'm just looking at that side. Okay? But let's just think about now on this side. Okay? And then we'll come back to that one. But that equation will be the yield surface, you agree, for this side, right? For the wet side. And it's just an equation of an ellipse. Let's check that this equation makes sense. Let's say that Q is equal to 0. What is going to be at yield the value of P prime? So if Q is equal to 0 and I want to make this equal to 0, I know this one is not equal to 0 and I don't want to go into the trivial case of this one to be equal to 0. Therefore, P prime has to be P0 prime. And that's exactly that point over there, right? So the yield surface equation is telling me that if I do an isotropic compression test, I'm going to reach the plastic limit or the yield stress at that point. What about if I'm at the shear failure line at this point on the top? I'm still looking at the wet side, and Q is equal to MP prime. And that, by definition, will be that point over here, right? According to the definition of M. What is going to be the value of P prime? You have to do some math, okay? It's not as simple as the one before, but it's not too difficult to solve. It's going to be 1/2. And that kind of makes sense, right? Because if you are at that point, your mean stress has to be half of the limit mean stress for the isotropic compression line. What is important to notice here, I'm coming back then to what Steve was saying, is that this value P0 prime is a variable. And it's more than a variable. It's going to be our hardening parameter. That's how we're going to track the hardening in the constitutive model. And that P prime, according to this model, also is going to be a function of porosity, or which is exactly the same. So lower porosity, stronger material, which is exactly the same, is going to be a function of the variations of volumetric plastic strain. And this is what we're going to get in a little bit. So let's try to see how this parameter would change if we were to do a cyclic loading test. So this is Q, this is P prime. This is the critical state line with slope M. And let's imagine that we have a material with an initial yield surface in this location, and we're going to look at the wet side. So what I'm going to do now is I'm going to start somewhere over here. I'm going to do a tri-axial test. So let's say that I do a tri-axial test in which I increase deviatoric stress, I pass the yield cap, and I stop halfway. I don't get to the critical state line. Let's see what will happen to the stress and strain. What this is telling me is that this is going to be elastic at the beginning. As I pass the yield cap, I'm going to start to see plastic strains. So this is going to start to deviate. And if I were to plot here volumetric strain, this one will be up to this point elastic, and when I get to that point I already have plastic strains, and this will bend a little bit like this. Okay. Do we agree so far about what has happened? All right, so now let's unload the material. So we first loaded this one. Now we're going to load it back to here, to the beginning. As we do the unloading, because we have gone through this initial yield surface, and because we had some plastic strains, what we're going to get are irrecoverable plastic strains. So now in this plot, what is going to happen is that as I do the unloading, this might come back somewhere over here. And I have this irrecoverable strain in this direction. And if I look at the volumetric strain, it's not going to come back through this path, but it's going to come back through a path which is somewhere over there. But now look, I have a change in volumetric strain which is irrecoverable and was associated with going over the yield stress. So it didn't come back over there. It just came back over here, and this difference now is what we have changed. That will be your delta EPP, volumetric plastic strain. So let's load this material again. If you load it one more time. Okay, before we do that, since we have moved over here, because of this change on volumetric plastic strain, now you're going to have a new yield surface. Because you went past that point and you cannot come back from that. Because you have this additional plastic strain, now your material has hardened because going through that, and now your new yield surface is going to be there. It's not going to be the one that was here before. And if you reload this material, in order to get again to the plastic deformation, now you have to go beyond that previous point. So that previous point, it looks like somewhere over here. So as you come back, now you will pick up again this line, and let's say that we continue all the way over here, and you will pick up this line, and if you go into the critical state line, it will just go in this direction. And if we pick up this one from here, so this goes in this direction, loading, unloading, and reloading. It will go into an asymptotic trend, and that asymptotic point is when you get over here. Let me add some color to this to explain these trends. So that would be the asymptotic state of stress. But every time you go onto this side of the wet side and you have some remaining plastic strain, you're going to change the yield surface. And look at, again here, we passed again the yield surface. So now the new yield surface is over here. So it's going to be another ellipse that now goes through that point. And now, if at this point I could unload the material and reload it again, and if we do that, it will just, so let's do that. So I unload that and I reload it, it will come back into the perfect plastic deformation. And here, it will just come down, go down in this direction and come back to here. But the important thing to get from here is that P naught is going to move. And the movement of P naught is going to be a function, as we were saying before, of this plastic strain. And that plastic strain, it's volumetric plastic strain, and if it's volumetric plastic strain, we can also link it to the porosity, or what it's mostly used in this model, something called the void ratio, where the void ratio is the ratio of porosity divided 1 minus porosity. I'll come back to this explanation, a physical explanation of the void ratio in a minute. So if the variation of the volumetric plastic strain is positive, that means smaller porosity as you go into this direction, and that means a stronger material after loading. If your variation of volumetric strain is negative, as in dilation here in the dry side, that means higher porosity, and if this one is negative, that will mean that the material is going to get weaker, and actually that P naught is going to move to the left instead of to the right. All right. Any question about this so far? Now we're going to get into the volumetric strains and the equations that we discussed before. We're explaining porosity as a function of stress. No? All right. So then I'll continue. Let's now try to use porosity or void ratio instead of volumetric strain into these equations, because many of these equations are written in terms of porosity because it's a more physically meaningful variable. Let me plot here deviatoric stress, mean stress, critical state line, and I'm again, I'm just going to consider the wet side, and I'm going to have a yield surface like this one. And I'm going to perform a test in which I'm going to compress a material isotropically. So if this is the initial condition, this is the final condition. Where would that stress path be in the QP space? On the x-axis, right? So it would be a path that goes, it could go, say, from here to there. It's an isotropic compression experiment. It turns out that, as we explained before for the case of these clay sediments, that the porosity, or what is equivalent, the void ratio of these materials, has a nonlinear relationship with stress. These materials are not linear elastic. They can be elastic sometimes, but they are nonlinear. And that relationship, it's either, as I share with you in the problem, it's a relationship which is either logarithmic or exponential. And what that means is that that line, if it's in linear scale, is going to be a curve. The higher the mean stress, the lower, notice that here I'm going lower in porosity or void ratio. And this is what is called the isotropic consolidation line, or ICL, isotropic consolidation line. It's an isotropic test. And it is nonlinear, okay? Let me explain the void ratio now, because I think now this is a good opportunity to explain the void ratio. If you have a material that you could conceptualize as being made of volume of the pores and volume of the solids, and this one is equal to 1, the definition of the void ratio is the volume of the pores divided the volume of the solids. And if this is equal to 1, this one is equal to porosity, and this is 1 minus porosity. So the void ratio is equal to porosity divided 1 minus porosity. I always forget this equation of void ratio. But you just have to draw this. If you draw that, it's natural, it comes out of that drawing. But it's a parameter which is linear with the porosity. So it is basically a porosity, but written in some other terms. So the higher the mean stress, the lower the porosity or the void ratio. That would be for an isotropic test. You could also perform a test that, or similar to what we have done before, in which you do not let the solid to contract in the horizontal direction, but you just let it contract in one direction, right? And we call that either 1D strain or Audiometer test. And that this is much closer what happens to sediments in nature as they compact and you have more overburden. And this is also closer to what happens when you, for example, deplete a reservoir, you lower the pore pressure, they compact in this way, not that much in that way. And in this case, if you remember, the stress path, it will be a line that, let's say that we start somewhere over here. Now, it has a slope, and it makes it crosses your surface somewhere at that point instead at this point. So this will be closer, we said, to sedimentation and burial, or it will be closer also to depletion. So that's a little bit more realistic. And for that line, there is going to be another line associated with this, which is going to be a line which is somewhere over there, and is going to be different than that isotropic consolidation line. So we can put these two plots now together, okay? And the result of this is going to be a relationship, a unique relationship that links the deviatoric stress, the yield surface, and the yield surface as a function of porosity. So the yield surface, because of this relationship, is a function of porosity. The point at which you cross that line is a point in which here, I hope this comes out okay, but if you were to do unloading, your unloading would be that line. And if you do reloading, your reloading will come back to this original normal consolidation line or normal compaction line. Yes, Steve?
For the stress test in the P prime Q for Audiometer test, why there's a Q initially?
Here? Because we're assuming we're starting at a condition, initial condition already with some anisotropy. You could start somewhere over here, okay? You could do that. Or you could start here at the origin. This could be the result also of over-consolidation, right? You put stress, then you take it out, and you have locked-in stresses. But let's try to put now this into a 3D model, okay? And that is going to help you conceptualize much, much better the relationship between the yield surface and porosity. So we're going to put this axis Q over here, P prime over here, and void ratio or porosity in this plot. For that, for a given condition, we know that we're going to have this critical state line, and this is a difficult plot, guys. So let's see if I can get it. I think I'm going to change this axis a little bit more so I can get a more 3D looking plot. All right, so this is going to be, wait a minute till I finish it so you can see what I'm plotting. Okay, not bad. So this is the isotropic consolidation line. When Q is equal to 0, that line is this line over here. And these over here are your yield surfaces, the half of the ellipse. And what this extended yield surface now in 3 dimensions shows is that the value of P naught, which will be the projection of this point onto this axis, is a function of porosity. And this is a line which is a line that goes into 3 dimensions, right? And this line, when it projects on the QP space, gives you the critical state line. And this line, when it projects into the EP space, it gives you the normal consolidation line. But basically, the important concept here is that the size of your yield surface, according to this model, depends on porosity. The higher the porosity, the more further apart the grains are, the freer they are to move, and therefore the yield surface is very small. If the porosity is very small and your grains are close together, very well packed, very small porosity, your yield surface is going to be much bigger. Let's see, what time is it? We have 15 minutes, 10 minutes. All right, so we need now to get into a few more equations in order to finish this model and to be able to predict an elastoplastic stress path. So let's do that. And for this application problem, I'd like to recall the example from the project. This is a natural compaction problem, compaction and burial, in which your porosity depends on effective stress. So your porosity, so you're somewhere in this line, depends on the effective stress, right? And for this case, what we have, it's what we have already been drawing for some time. If we go to a marine sedimentary basin, we know that we are depositing sediments, and those goes into layers, and as though those go through a process of burial, then they get compacted just in one direction. We want to explain this with this fancy new model that we just